Hi everyone. In this video lecture, let us solve a problem based on free convection in a water glass. Initially, the glass have water at 5 degrees Celsius. Since it is a rotational symmetry problem, we just converted the problem statement into two-dimensional axisymmetric problem. I have just taken this portion of the problem. This portion I have taken. Since it have rotational symmetry, then the dimensions of this geometry is given here. Radius at the top, radius at the bottom, height of the glass guard, then thickness at the sides, thickness at the bottom, and this length is calculated based on the formula given here. That is this radius minus this radius square, then take square root of that plus this height. It is calculated. I'm going to draw this geometry in COMSOL using polygon dimensions. I'm going to do it in two steps. First, I'm going to draw it inner geometry. Then I'm going to draw it outer geometry. I'll explain how this polygon can be constructed in COMSOL here. Then I will directly import the file which I already have. So nothing but I need to connect the 4 point. The first point here is I have to for the 2 point for the given point you need to mention two dimensions here. That is radius equal to 0, this position, and h bottom. From here to here is the h bottom. So this is my first point. Then the second point will be this point. By excluding the thickness of the wall, nothing but it is calculated by r bottom minus h wall, that is thickness of the wall. Then from here to here. So I'm just locating this point. Similarly, I'm locating this point. You can refer these points here. I'm locating this point here. Connecting all those points, I will form a inner geometry. Then similarly, we can draw the external geometry. Now let us solve the problem using COMSOL. Click on what is that, then and select a two-dimensional axis symmetry. Then expand fluid flow. Under that, select non-isothermal flow. Expand, then select laminar flow. Add click study. Then select time dependent. Done. Now click on parameters. Load the file. You can also manually type those parameters. Open. So these are the data we already have, the text file. Now let us click on geometry or click it here and select polygon, and I'm going to load the already pre-existing file in. These are the data which I already have it in the paint. Now build all objects. So we have constructed inner geometry. You can see here from 0 to some space, some height is here. Now again click on polygon, drag down, load the file, outer, open, build all. Now we have constructed our two-dimensional geometry. Now let us select the material. Click on material, and here type glass, silica, glass, search under built-in material, select silica glass and add to the component. Since my outer body is the glass, I'm going to unselect the inner body. Now again go to the add material, type water, click on search and select water liquid. Add to the component and select my water component, and here just create selection, click on that, type water, it's okay. Now we have added the material, then click on laminar flow and I'm going to select only water from all the domains. So I have selected water here. Then I'm going to select my compressibility as incompressible flow. Since water is incompressible, I selected. Then include gravity, and it will ask what is the reference point of the gravity. So I'm going to select this point as my reference point. So I'm going to give my radius will be r r r top minus thickness of the wall, and this position will be my h g h g. I give the reference point. Now next thing is uh, click on physics and under points select pressure point constraint. I'm going to fix this point as a pressure constraint and let me select point number 6. That's all. Then I have to select the wall because by default wall 1 contain this this space, this space and this space, but these two belongs to the glass. This is exposed to the air. So I'm going to create another boundary or wall, and I'm going to select this as my wall, and I'm going to select wall condition as slip. That's all. Now drag down under multiphysics, select non-isothermal flow and select this box that assume this equation assume density is the only function of temperature. Then let us click on add property. I'm going to define my atmosphere property, that is ambient, and that will be my let me assume atmosphere temperature is 298.15 Kelvin. Now click on under heat transparent fluids. Let me select initial value. Initial value let me take 290, sorry 278 because it is initially at 5 degrees Celsius, 78.15 Kelvin, and I'm going to, since it is a mixture of both fluid and solid component, under domain select solid and let us remove, let us select, yeah, this is my solid component, that is done. That is a then let me define the temperature. We need to define three boundary conditions here, here, and here. First, let us define the temperature at the bottom, which is placed on the table, and select boundary, select temperature, and select this bottom boundary. And this is nothing but ambient temperature. Then at the side, we have heat flux due to the natural convection. So let me select boundary again, select heat flux, and let me select this boundary. Then I need to select heat flux as the convective heat flux. That is a problem statement. Drag down. Then heat transfer coefficient. It is external natural convection, and here, what is the position of my glass rod? Sorry, glass here. For that, this select here. It is inclined. Let us select inclined wall, and that last what is the length of this glass? V already we have calculated V length and angle, which is mentioned by here. This is theta. This is nothing but the cos theta, A cos, and this distance, that is vertical height, divided by the inclined height, which is nothing but h g divided by v length. Yeah, we have given the angles. Now let us select another boundary at the top, heat flux again. Here only the heat transfer takes place from fluid to air, and here conduction is dominant. This conduction at the top. There is a formation of air layer. So here instead of taking heat transfer coefficient, I'm going to take the conductivity of the air layer at the top as the heat transfer coefficient. So let me select one by one. What is the convective heat flux? Then let me select H value as 2, that is nothing but the conductivity of air layer at the top. And I need to select the boundary as well. That is my boundaries here. And they are small boundary. Let me select that by zoom to select. Let me select all the points, all boundaries, and let me reselect. Uh, so it is 8. Okay. Let me manually select manual. This okay. Clear. This point. Then I need to select. I need to select this point. This is my point I want to select. Now I select the file 8. Even though it is not a airline, it may assume it is very small thickness, and that's all. We have given both the heat flux and the boundary conditions. Now let us mesh, create a mesh. Click on mesh and click on mesh one, and here let us select by default physics controlled mesh, and the element size let me take 5, and build mesh. Click on build mesh. Let me select final build mesh, and click on uh, zoom extends so that we can have in the same size of window. Now meshing is done. Now come down under study time dependent. Here let me change the timing 0 to let me have every 3 seconds. 3 seconds within the square bracket. Just give yes, indicating seconds in units. And still I want to conduct for 2 minutes. 2 minutes. Then the tolerance value, let me manually give 1 e power minus t. Before that, let us save the file glass. Then and now just on the study, click on study, click on show default solver. Now expand solution 1 under time dependent solver. Here, let us select uh, my absolute talent. Let me expand that. And factor, it is a manual. Let me give values as 2.5 e power minus 5. Yeah, everything is done. Now click on complete. Yeah, by default, we have a velocity profile, and temperature profile is not by default is created or two-dimensional. Let us create that by adding the plot group. Click on the cells, click on 2D plot group. Now 2D plot group, we need to yeah right click on 2D plot group and select surface, and here under the expression we have replace expression. Select that heat transfer fluids and select temperature, and let us select degree Celsius. Under coloring table, we can expand thermal and select heat camera light. Click on OK. Just click on the plot. We can have the temperature profile. The minimum of 6 degrees Celsius. Minimum around I think 5 degrees Celsius. 6 it should be because we have this data have been obtained at 120 seconds. Similarly, you can change the time seconds, whatever time you want. Let me select 30 and you click on plot. You can observe different temperature profile. And let us now create the velocity streamline. For that, click on the cells to the plug in and right click on the streamline and the velocity and come down under positioning in the list. Select starting point control and come down. Color, let us select blue because water is in blue. Then yeah, yeah. Now plot. So we have the velocity streamline, and then we can change a different second, like from the under 2D plot group. You can select different time. We can select that T and the plot. We can observe the difference in the streamline of the water. So now I've done both velocity profile. You can, if you want to see the velocity, you can expand this and turn surface. You can see the velocity profile as well. Now let us find the values. For that, let us create the tables. Before that, click on results and come here under numerical. Select no derived values and select line integration. And we need to select the boundary. Let me select. Uh, Let me find the uh, heat flux at the bottom here under expression, replace expression. I want to find the heat flux at the three different boundaries. Uh, Here, heat transfer fluids, boundary fluxes come down normal total heat flux. Let me name it as bottom heat flux bottom. Similarly, let us create another two boundaries, more data set. Yeah, sorry, numerical, more derived values, line integration. This boundary replace boundary fluxes above normal total heat flux. Yeah, heat flux side. Yeah, you can evaluate this one. Evaluate, you can have the heat flux value. So you can generate at different time what is the heat flux. Similarly, you can evaluate here as well. Yeah, an active sign means it lasts surrounding. Okay, then again let us create for the top numerical, more derived values, line integration. Let us write top boundary, replace expression, boundary fluxes, come down, normal heat flux. Yeah, now let me rename it as heat flux top. Click on evaluate. Now let us plot the table for that uh, under results 1D plot group. Right click here, table graph, table 1, and we can manually here we can manually select x-axis variable time and the y-axis normal topic heat flux, and also title also can be manually given heat flux versus time, and also the spaces can be manually given. Let me give 20 seconds, 20, 20, and class. So that's what I have heat flux this time, and we come down and show the legends. Here also table graph also just come down. Yeah, expand legends and show the legends again. Right click on that uh, table graph. Now let us select table 2 and here. So the legends come and let us align. Let me give dash so that we can observe the difference. And color, let me give magneta and the plot. So we can see the color. And similarly, let us create another table graph. Of, table graph. Now let us select table 3 line dash and the color let me select now red and the soul legends class and select my class group. Come down legends. Let me select middle right so I can bring the legend. This is the temperature. Sorry, heat flux profile with respect to different time. The space out every 20 seconds. Thank you for watching the video. Thank you.